The beaches. The shoreline has been defined as the boundary between the water and the land. How dull and lifeless this definition is in relation to what is to be seen and felt where the land ends and the ocean begins. For here, at the shore and along the cliffs, we see the struggle between the forces of erosion and the forces of resistance and construction. One seeking to tear down the land, and the other trying to stop the onslaught of the waves and currents and to build up the land. Here is the place of supreme peace and calm when the elements are at rest, and the place of wildly raging surf and fierce winds in times of storm. In the waters near the shore, we find the birthplace of millions of marine creatures and, on the strand line, the shattered shells and carcasses of animals which nature has discarded. The beach is that part of the land that is covered with water-worn sand and pebbles, extending in most places from low water mark to high water mark, and a little beyond. It is a place of constant change, of sorting and mixing, cutting and filling, grinding and rounding. Even on a calm summer day, the lapping of the small waves on the beach tells us of some activity there. In Prince Edward Island National Park, we have a little of all these things, and we can watch many interesting processes in action. Grains of sand. Let us look carefully at the sand on the beach to see what it is made of before we see how it is distributed and what forms it takes. Pick up a handful of sand on any beach in the park and look at it very closely. What we are doing is leaving the world on our scale, where objects are measured in inches and feet, and moving in for a closer look at a world where things are very much smaller. Grains of sand are measured in hundreds of inches. And the rare pebbles which are half an inch in diameter are large objects. A pinch of sand from somewhere on the beach where it is dry, spread onto a piece of dark paper or cloth so that the grains are separated a little, will show you many interesting things. Even with the naked eye, you will be able to see that the grains are all about the same size. You may see that some are angular and some are rounded. Some grains are clear and glassy, some are pink or red, and others are black. On some parts of the beach, tiny flakes of a shiny white mineral are visible. The mineral quartz is by far the most abundant of all minerals in sand. In the Prince Edward Island sands, most of the quartz is the clear, glassy variety, although you may also see some white or milky grains. When quartz of any of these kinds is coated with hematite or iron rust, it becomes pink or red. The black grains are made of magnetite, an oxide of iron. The shiny, flaky, lighter-colored mineral is muscovite or white mica. These very beautiful beaches have resulted from the accumulation of great quantities of almost pure quartz sand, and are different from most beaches in that they contain hardly any other minerals. Sands in other places may include fragments of many other kinds of minerals and of fine-grained rocks. Why quartz is the most common? The processes that produce sand may be simple or complicated, but they all require that a rock be worn away in one place, and that the resulting debris be carried off to accumulate somewhere else. If the breakdown of the original rock is by purely physical means, such as splitting by frost or grinding along seacoasts, the fragments may exactly resemble the rock and mineral grains from which they came. Most rocks, however, are made of a variety of minerals in varying proportions. Some of these minerals may break down chemically when they are exposed to the weather. Everyone knows how iron rusts away gradually when it is left unprotected. Suppose a rock were composed of a mixture of minerals, and some of these minerals were broken down physically, and some were altered chemically. One would expect the debris from the erosion of this rock to be a mixture of grains, some looking like the original, and some quite different because of the chemical changes. The most common of all minerals in rocks are quartz and feldspar. Quartz is a hard, glassy, or white mineral which is very resistant chemically and very tough physically. Feldspar, on the other hand, decays rather readily under ordinary conditions of weathering, even though it is fairly hard. Thus, most rocks that are weathering at the surface of the earth will go to pieces gradually with the breakdown of feldspars and other chemically susceptible minerals, and the breaking off of bits of quartz without change. After the original breakdown of the rocks, the next stage in the development of sands is the transportation of the materials of weathering. The grains may be swept into a river system or into the waves and currents along the shore. Soft grains are worn finer and finer by abrasion, and the more resistant and tougher ones, such as the quartz grains, generally last much longer. If the materials have come a long way, then the process of separation will be more complete than if the distance of transport is short. Beaches and bars consisting of highly pure quartz sand would thus indicate that the stuff they are made of has survived a long and rugged history. It is intriguing to think that we may be looking at the graveyard of a chain of mountains as we scan the wave-swept beaches. Figure 4. Ripple marks formed by the rhythmic motion of water in waves are symmetrical. These ripples have been rounded off on their crests as the water retreated. Patches of pebbles interfere with the regularity of the rippling. Some erosion of the ridges has taken place just below the shell. How some sand is that way twice. It very commonly happens that beach and delta deposit of sand become hardened into solid rock. If this rock eventually becomes exposed to erosion again, the same grains of sand may be loosened out of the second rock and washed back and forth again by waves or currents. It is almost safe to say that most beaches with nearly pure quartz sands are of this kind. In Prince Edward Island National Park, the reddish sandstone and siltstone of the underlying bedrock have contributed much of the sand. It is probable that the sands on the bottom farther out under the sea have also come from the breakdown of similar rocks. This means that the sand grains were blowing about, or were being carried by water in motion in the seas and rivers of 250 million years ago. That they then became part of the solid rock, and then were torn loose and washed about all over again. Now, pick up a handful of this ordinary sand and scan the grains with this long and complicated history in mind. Processes of sorting on the beach. No matter how small a wave is, as it sweeps in on a sandy shore, it disturbs and rearranges some of the sand grains. Light grains are moved about more than heavy grains, and small ones more than large ones. Once lifted from the bottom and put into temporary suspension in the water, lighter and smaller particles take longer to settle again than heavier and larger particles. This holds true no matter what the cause of disturbance or how powerful it is. You can actually observe this differential agitation by going down to the shore and wading out to a place where the water is about 8 inches deep, with gentle waves coming in. As each wave passes, you may see through the clear water how the sand is stirred up and how it settles out. Some grains settle out at once, but others take a few seconds longer. The very fine particles of mud and clay have long since been carried off, but if they were still here, they would probably stay suspended for a long time, so that the water would appear muddy, even from a distance. Figure 5. Currents formed along the shore, or due to the return waters of breaking waves, produce asymmetrical ripple marks like these. Notice how the larger pebbles and grains are more conspicuous in the hollows and the finer grains are in the crests. A snail's track is clearly visible, leading from one end of the jackknife along the flank of one of the ripples just below its crest. The large pebble above the knife has interfered with the ripple pattern. Ripple marks. When water is in motion over loose sand, the surface of the sand is formed into ripples. These structures you may see along any of the beaches of the island. They are present in the beds of small brooks that empty into the sea across the beaches. They can be seen in great abundance on the flats left by the receding tide. They are well developed on the sea bottom to depths as great as 30 feet and more. When you are swimming, they may tickle your feet. Ripple marks are of two kinds, symmetrical and asymmetrical. This means that one type is formed of peaks with troughs of exactly the same shape on either side, and the other type has peaks with troughs that are not the same on the two sides. It is common to associate the symmetrical ones with waves and the asymmetrical ones with currents, but close observation will show you that waves may cause either kind, whereas currents will only cause the asymmetrical ones. When currents become very swift, they produce the whirly pattern ripples seen in Figure 6. Figure 6. The shapes of ordinary ripples, in which the ribbing is at a right angle to the flow, are changed to this whirly pattern when thin sheets of water, such as in a shallow brook, flow swiftly over a muddy or sandy bottom. In small streams crossing the beaches in Prince Edward Island National Park, such as the one on Cavendish Beach, these ripples are visible in all their rapidly changing shapes. Whether waves produce asymmetrical or symmetrical ripples depends entirely on how they are breaking and the shape of the bottom. In some instances, you can stand with the gentle waves lapping about your feet and watch symmetrical ripples change to asymmetrical ones in a fraction of a second as the wave changes shape during its exhaustion on the shore. Symmetrical ripples are more common in deep water. In shallow water, the sharp forward motion of the wave is counterbalanced by a more gentle but longer-lasting backwash current. The exact depth at which the change from one to the other occurs depends on the shape and size of the waves. Distribution of grains in ripple-marked sands. The constant disturbance and rewashing of the sands, the action that forms the ripples, also tends to separate minerals of the sand. You may see this by examining closely some well-formed ripples. Black grains of magnetite are commonly much more abundant near the crest of the ripple than in the trough. Coarser particles, bits of shells, and pebbles may be left in the troughs. Light fragments are found in greater concentration on the front of the steep face of the ripple than anywhere else. In the gentle waves of the shallow water, you can watch this process of separation actually working. Preservation of ripple marks. As the tide recedes, the ripple marks found on the bottom come closer and closer to the surface. They thus become more and more liable to erosion by currents as the shapes of the waves change and as the rhythmical wave motion changes to a series of currents. As the ripples come to the surface, their tops are planed off and their troughs become filled. Most ripple marks are completely obliterated by the time the tide has left the former bottom dry. Points of interest. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Up and down the beaches of Prince Edward Island National Park, you will notice large areas of beautifully rippled sands. How were they preserved? There are 3 ways. The first has to do with slight shallowing of the water offshore, which you may notice as you wade out for a swim. In such an area, ripples may be formed all over the bottom during a time of high water. As the tide goes out, the waves breaking on the receding shoreline may destroy the ripples as they come close to the surface of the water. On the other hand, one of the offshore bars may cut off the waves as the water gradually goes down, so that the ripples are preserved in a pool of quiet water behind it. As the tide goes out still more, the water in the pool may drain off to the side, or sink through the porous sand and leave the ripples completely exposed. Sometimes breezes on the surface of the pool stir up small waves, which in turn start new ripples on the bottom. These may be superimposed on the ripples developed earlier, and make complex patterns, as shown in Figure 7. Figure 7. An almost endless variety of patterns of ripples is formed along the Prince Edward Island beaches as changing waves and currents superimpose patterns on patterns. In this area, asymmetrical current ripples were formed by waves moving to the left. As the tide went down, the wind blew up small waves, which started to form ripples with their main motion towards the observer. Another way that ripples are preserved is related to periods of waves and calm. Suppose waves are piling ashore during a stormy period and ripple the bottom sands. If the weather changes suddenly and a complete calm follows, the tide may leave well-preserved ripple marks on the exposed flats because there are no waves to destroy them. It commonly happens that ripples are preserved over large areas if the bottom slopes downward from the beach to a flat area, which is above low tide level. In this case, the waves are prevented from destroying the ripple marks that were formed when the water was deeper. The waves cannot sweep across the shallow water on the flat with enough force to disturb the bottom. Instead, they break on the outer edge. As the tide continues to recede, the water drains off the rippled area and leaves it exposed. Interference with the rippling of sand. Ripple marks are best developed on beaches and bottoms that are covered with clear sand. Pebbles and bits of shells scattered among the grains of sand interfere with the formation of ripple marks. In Figure 5, a pebble clearly has altered the pattern of the rippling, not only close by, but also farther along in the down-current direction. With symmetrical wave rippling, the influence of such foreign bodies is not felt as far away as it is in current rippling. If rippling in one direction is followed by rippling from another direction, the patterns produced by the first interfere with the formation of the second. Interference patterns result if the process is stopped before the first set is completed. Interference patterns result if the process is stopped before the first set is completely obliterated. They also result when two sets are being formed at the same time. This could happen when a current is setting along the shore in one direction and waves are moving in another. An almost endless variety of combinations of ripples and patterns comes from conditions like this. Figure 8. Pebbles and shells rest in small depressions eroded in the sand by moving water. The delicate white lines are swash marks. Tiny ridges of quartz grains, mica flakes, bits of shell, and organic matter that mark the farthest line of penetration of individual waves. Figure 9. Rill marks are made on beaches when water oozes out of the saturated sand at low tide and returns to the sea, or by leakage from pools behind bars of sand. Notice the patterns produced by the shifting channels. The pencil gives the scale. Fossil ripple marks. Geologists have discovered rippled surfaces on sandstones in many places. These were laid down in ancient seas as much as 1 billion years ago. indicating that the processes we have seen on today's shores have been going on for a very long time indeed. Swash marks. Where waves wash onto sandy shores, they often leave delicate little lines of debris at their farthest shoreward penetration. These are called swash marks and are very well shown on many of the sandy beaches of Prince Edward Island National Park. If you go down to the water's edge and watch closely, you may see how they are made. As the water from the last forward motion of the wave washes up the gently inclined surface of the sand, it carries a load of tiny particles on its leading edge. When the forward motion of the water finally stops, some of the water sinks into the sand, and some of it runs back down the slope. Whatever it was carrying on its leading edge is left stranded as a swash mark. On some of the island's beaches, swash marks are made of grains of white mica, glassy and milky quartz, bits of mussel and clamshells, and other light fractions of the beach material. These swash marks appear as light lines on the darker beach sand, as in Figure 8. In other places, the swash marks are made up of almost exactly the same materials as the rest of the beach, so they appear only as minute ridges of sand. Each wave covers a slightly different area from the ones before, so that the swash marks appear as overlapping patterns, with only the last one complete. When the tide is rising, one would expect the swash marks to be erased gradually and replaced by later ones higher up the beach. But when the tide is receding, waves would reach less and less far up the beach, so that the area of swash-marked sand would gradually widen. One would hardly expect such delicate structures to be preserved when sands are solidified into rock, but geologists occasionally turn up ancient rock surfaces with swash marks clearly shown. Rill marks. When the tide comes in, water fills the pores in the beach sand up to the high tide mark. As the tide goes down, some of this water may leak out of the pore spaces and run back down the slope to the sea again. The marks made by such returning water, or by water that comes into the sand as rain or as seepage from ponds or lagoons at the back of the beach, are called rill marks. They are often branched with plant-like patterns, as in Figure 9. Figure 10. When waves break onto shallow, shelving, sandy beaches, the water moves forward to its maximum penetration, then reverses direction and flows back down again. As it gathers speed down the slope, it forms patterns like these, above and around pebbles. The sand may be seen in motion as the water swiftly erodes a little hole behind each pebble and makes V-shaped patterns outward from them. Figure 11. When the receding waves are gone, the sand may be patterned like this, with the pebbles lying in their eroded depressions and the V's clearly showing beyond them. Patterns and hollows around pebbles and shells. As waves sweep in on beaches, they tend to flatten the sand into smooth surfaces. If pebbles or rocks occur on the surface, the flattening process is interfered with. This is because the return part of the wave is in the form of a swift current running down the beach. As the current of water is forced around a boulder or a pebble, its velocity is increased immediately adjacent to this obstacle. so that it tends to scour the sand from around it. The resulting mixture of sand and water moves down current where the sand drops out and settles on the bottom in a V pattern, nicely shown in figures 10 and 11. Sometimes several collinear V's are formed by the currents, and any variety of compound patterns may result when several such simple patterns interfere with one another. Under certain conditions, the patterns may be different. Behind each pebble, a small area is protected from the moving water and is left as a little ridge. The V patterns do not affect the immediate bottom, but occur some distance farther back, where they may appear without the pebble being actually part of the V itself. Streaming out behind the protecting pebbles are long trails of sand grains that are a little different from the surroundings. This condition is partly responsible for the complicated pattern in figure 12. Trails and tracks on the bottom, wiggly lines, curved lines, branching lines, and straight lines, marks of slow-moving snails and other bottom creatures, are common on soft sedimentary materials. The track along the crest of the ripple in figure 5 was made by a snail. Tracks of wading birds and seagulls are often found on the beach and add their stories to the many others imprinted on the muds and sands there. Figure 12. Here is a complicated pattern on the beach, which has been compounded of interfering ripple patterns and the erosion patterns of retreating wave water around pebbles and shells.